All right, welcome ladies and gentlemen. This is video number 7 in our bonding videos. This is video is about polar molecules. You'll need your notes open to page 46. So as a bit of a review, polar as a term, remember polar means different, right? Opposite, asymmetrical, things like that. And we talked about polar bonds, but we can also have polar molecules as well. A polar molecule is a covalent molecule where one side of the molecule is different from the other side. So instead of the difference now being a difference in electronegativity, which it is with the bond, now it's looking at the entire molecule as a whole. Is one side different from the other? We call a polar molecule a dipole, meaning two poles. It has two poles. It has two ends. One side is different from another side, so two different sides. And these two poles, these two sides of the molecule, one side will be slightly negative, one side will be slightly positive. This is similar to our polar bonds. It's just now the entire molecule has one side that's slightly positive, one side that's slightly negative, instead of just the individual bond. And the way you determine if a molecule is polar, it's all about symmetry, molecular symmetry. So we look at that central atom and we say, is everything symmetrical around that central atom? If it is unsymmetrical or asymmetrical, meaning everything around the central atom is not the same, then it's considered a polar molecule, because polar means different, polar means asymmetrical. But if everything is symmetrical around the central atom, if everything is the same, then it's a nonpolar molecule. So this acronym SNAP is very, very helpful to remember with molecular polarity, because SNAP, if it's symmetrical, then it's nonpolar, so these two go together. But if it's asymmetrical, then it's polar. And whenever we're talking about this symmetry, we mean around the central atom. So around the middle of the molecule. That's where we're looking. So polar molecules. Well, first of all, big point I want to make is that you can't have a polar molecule unless you start with a polar bond. There's no way to create this slight positive and slight negative unless you start with the difference in electronegativities in the bond. So your molecule has to have polar bonds in order to be a polar molecule. There's no such thing as a polar molecule with nonpolar bonds. It can't exist. You have to start with polar bonds. But the polar bonds have to be arranged in such a way, so now we're kind of looking at the entire molecule. It's sort of the shape of the entire molecule. Polar bonds have to be arranged asymmetrically around the center of the atom. Right? So it's not just enough to have polar bonds, but if the polar bonds are actually arranged symmetrically, then we have a nonpolar molecule, because nonpolar means symmetrical. But if our polar bonds now are arranged asymmetrically, then we have a polar molecule. Again, you're looking at the central atom, and that's the really, really big point here. Look at the central atom. If everything that's attached to the central atom is identical, right, that's symmetrical. That's nonpolar, right? Symmetrical is going to mean nonpolar. But if you look at that central atom and you notice that there are differences, it's bonded to different elements, or even if it has lone pairs count as different things, right? If you have water, it's got 2 lone pairs on the oxygen and 2 bonds to hydrogen. Those are 2 different things. So that is an asymmetrical molecule, and that is definitely polar. So we're looking at that center and we're saying, hey, is everything the same? Yes or no? So some examples of polar molecules. So these are all asymmetrical. We have asymmetrical distribution of charge around the central atom. So if we look at, for example, HCl, notice, right, 2 different sides. That's what polar means, asymmetrical. So boom, you have one side that's H, one side that's Cl. Next up is water. Again, look at the central atom, which is our oxygen. So look at the center. And then look at everything that's attached to that oxygen. Yes, we have 2 bonds with hydrogen, and that's the same. However, we also have 2 lone pairs. Because these 2 things are different, that is enough to cause the asymmetry. If you draw a line here through the water, notice that this side by the oxygen is different from this side by the hydrogen. That's polar. There are 2 different sides. There's a side with the lone pairs on the O, and there's a side with the H's. It's not the same all the way around. It's polar. Looking at this last example, again, you always want to focus on the central atom and say, is everything the same around it? Well, this is a polar molecule, meaning everything is not the same. So yeah, I have these 3 bonds with hydrogen. Those are all the same. But then I also have this bond with fluorine. So because these guys are different, different means polar, that leads to the asymmetry. And that's why that compound is a polar molecule. Now some examples of nonpolar molecules, some things that are symmetrical, because that's what nonpolar means. Symmetrical. Symmetrical distribution of charge. So we start off with oxygen, O2. Notice how it's the same on both sides. It's symmetrical, it's even, everything's the same. Next up we have CO2. So we have our central atom. And yes, the C to O bond. This bond, if you just look at the bond, this is a polar bond because we have two different electronegativities, right? This is absolutely a polar bond. However, notice that we have the same polar bond on both sides. That everything that's attached to that carbon is identical. So these two sides are the same. So therefore, this is a molecule that's symmetrical. This is a nonpolar molecule. Likewise, our last example, this is a nonpolar molecule. So we look in the middle, look at our central atom, and then we pay attention to everything that's surrounding it. And notice that we have the exact same thing on all four sides. It's even, it's symmetrical. So it's nonpolar. That's what nonpolar means. So a question, this is a very standard, very typical Regents chemistry question. Which formula represents a nonpolar molecule containing polar covalent bonds? I am just going to go through before I get started and add in some lone pairs because they didn't transfer. So I'm going to add in the 2 lone pairs on each oxygen. I'm going to add in a lone pair on the nitrogen and 2 lone pairs on the oxygen and water. But other than that, the bonds are the same. So first question, which formula represents a nonpolar molecule? That's important, containing polar covalent bonds. So if we look at choice 1, notice that we have the same element in the bond. That means that the bond itself is nonpolar. This can't be the right choice because we need to have polar covalent bonding. Now, if we just focus on the bonds, notice how if I'm just focusing on the bond, I don't look at the entire molecule. I just focus on an individual bond. That's all I'm doing. In all these other 3 cases, I do have polar bonds. I do have 2 different elements involved in the bonds. So, okay, so that's good. So I know that at least choices 2, 3, and 4, they're all polar covalent bonding. So that works. Now I need to go to the nonpolar molecule bit. So I'm down to choices 2, 3, and 4 for which molecule is nonpolar. Nonpolar molecule means symmetrical, around symmetrical distribution of charge around the middle, around the central atom. So now I'm going to look at the central atom in each of these cases and I'm going to see what's bonded to it. So in carbon dioxide, I have a C bonded to an O and then a C bonded to an O. That's the same on both sides. That's going to be good for us. For NH3, I have an N that's bonded to an H, but then I have a lone pair. These guys are different from one another, right? I've got 2 different things that are attached to my central atom. I've got H's and I have a lone pair. In water, I have an H that's attached to my oxygen, but then I also have lone pairs. Again, these guys are different. Polar means different. Nonpolar means the same. So choice 2 is the correct choice because I have a polar bond, but the molecule itself is symmetrical around the center atom. So that's my nonpolar molecule. Now, a big thing about polar molecules is that because the molecule has these partial charges and partial positives, partial negatives, you actually have an attraction with these molecules to an electric field. You'll notice in this picture here on the left, our electric field is turned off. So the molecules are kind of random in terms of how they're arranged. But as soon as you turn the field on, notice we have the positive plate and we have the negative plate. Now all the partial negatives, they're all facing the positive plate, and all the partial positives, they're all facing the negative plate, they're lining up. So polar molecules, because they have these partial charges, they can actually line up in an electric field. So that's our notes on polar molecules.